So we left off last time tackling this circuit, and we'd come up to the point where we're going to do the inverse Laplace transform, but I want to very quickly recap what we did. On most problems, unless we're just flat out told that there's no energy storage, and we're going to have an example coming up like that, where we're told there's no energy storage. That makes this step very easy, but on most problems you have to go through this step, and you have to look at, well, what happens when t is less than 0, or sometimes we might say that t is equal to 0 minus. You can talk about it both ways. And what we're going to do is we're going to look at that inductor then as a short. The resistor stays, the switch is closed. We have this voltage source here, 12 volts, 4 ohms. We have this voltage source, 12 volts. A cap is going to be open, right? An inductor is going to look like a short. The cap will look open. We have that resistor. So then our task is to come up with this current. We might say I sub L, and this voltage across here, V sub C. And the polarity of the voltage and the direction of the current are important, so we want to remember that. We went through that last time. For the details on that, you can look at last time's lecture notes, although it's not too tough. I sub L turned out to be 3 amps, and V sub C turned out to be equal to 24 volts. Okay. So we did that, and then we said, kind of segregate this off to the side here, and then we said, well, okay, so let the fun begin. We'll take t equal to 0 plus, or if we wanted to, t is greater than or equal to 0. Maybe we should just say greater than 0. And we did this a couple different ways, and I'll recap those two ways. We did it here in the time domain. We looked at the circuit in the time domain. When that switch was open, the circuit looked something like this. One farad capacitor is not realistic, makes our numbers easier. 2 ohms. 4 ohms, 2 henries, probably not realistic either. 4 ohms. And I said that I'm going to look at this current going around here, and I'm going to talk about this as I of t. And with that, I got everything there. I used Kirchhoff's law and developed the expression that I had L di of t dt, because that was the voltage drop across that inductor, plus 10 I of t, that's the voltage drop across all the resistors. 2 4s and a 2 gives me 10. And then I had this gain here, so I'm going to subtract 12 because that's a gain. And then I had the drop across the capacitor, so I have 1 over c, which c is equal to 1, times the integral of I of t dt. And then I need to add the constant there, plus Vc of T naught. That got me back to 0. Okay. So with this, I could substitute in the values. L took on the value of 2. I think this initial value across here was the 24 that we got from there. This C was 1. Okay. And we came up with an expression 2 di of t dt plus 10 I of t plus the integral of I of t dt is equal to minus 12. And we took the Laplace transform of that. And when we did that, we came up with 2 times si in the s domain minus I t naught plus 10 I in the s domain plus integration. That was always the great bargain, right? It's I to s divided by s is equal to minus 12 over s. And we had to be careful here. We substituted in for this piece that was a -3. And the reason that that was negative is we look at this current going this way, whereas this I sub L was calculated that way. So that's what that negative sign comes from. Those two negative signs will cancel each other out. And when you get done with this, and I'll just skip to the end step here. I had this in more detail in the last lecture, but you'll have -3s minus 6 divided by s squared plus 5s plus a half. And that's what I in the s domain looks like. Okay, so at this point, that's where we stopped, and we said, well, we're going to have to talk about how to take the inverse Laplace transform, right? The other thing we did, and it's probably worth looking at, I'm always a little more comfortable thinking about this in the time domain, but we may want to look at this in the S domain, and I'll go through this. I did it in more careful detail last time, so you could refer to that lecture, but I wrote it in the S domain. So essentially, I've already taken, as I draw this circuit, the circuit's in the S domain, I've already taken the Laplace transform of it, and we talked about the different elements in the S domain. So that inductor has this voltage source that's in series with it, and that's L times I 0. This is S times L. The the resistors are the same. The source, we have that 12 over S indicating the switch. 4 ohms there. Another resistor that stays the same. Then the capacitor, that's 1 over S times C, and then it has a voltage source that is V0 over S. I have the 4 ohm resistor down here. And again, I took this current here. The only difference is now this is not I of t, but it's I of s. So going through Kirchhoff's law in a very similar fashion, I could say that I have minus L I naught, because that's a gain, plus then the drop S times L times I of s. That's that one. Then I have plus 10 I of s. That's all the resistors, 4 plus 4 plus 2. That's another gain, so I'll subtract off 12 over s. And then I have to add to this what I s divided by sc. That's that piece right there. And what's that? That's also a drop, so V0 over s gets me back to my starting point because I've dealt with that resistor in this term here. So I can say that's equal to 0. We make some substitutions here. L is equal to, what did we say, 2. And C was 1. And this was, do I have that one? This one here was minus 3 for the same reason that this current is going up like that and not down like we found it. And this was what? This turned out to be 24. Okay, so when you tidied this whole thing up, and I go through it in a lot more detail in the last lecture, I'm not going to go back through that again, but you came up with the same expression that I in the S domain, when you solve for that, is equal to minus 3s minus 6 divided by s squared plus 5s plus a half. I think that's exactly the same as what we got there. Yeah. Okay. So then we have to take the inverse Laplace transform. And you're not necessarily going to do it both ways. I think even if you're, as an electrical engineer, if you're more comfortable thinking about that, that's fine, but you probably need to recognize this because someone's going to come along and talk about that. So you should be versed in both of them, even if you choose not to use this one. So let's talk about, assuming, are we okay at this point? Okay, let's talk about how we finish the problem. In either case, we need to take the Laplace transform, the inverse Laplace transform of that. So let's see what that looks like. So I think what I will do is, yeah, let me just go ahead and start with that. I'll start on a clean piece of paper. So no matter which way we go, we end up trying to solve for this, that minus 3s minus 6 divided by s squared plus 5s plus a half. And we did some work to make those polynomials look nice and neat, get rid of the leading coefficient in front of the s squared and things like that. So it's really ready to be factored, right? So I'm going to look at this piece, talk about factoring that. I'll use my quadratic equation. So this is what ax squared plus bx plus c. We get, thinking about that, what's that turn out to be? Minus b plus or minus the square root of b squared minus 4ac all divided by 2a. That's what we're going to use. So I have minus 5 plus or minus the square root of 25 minus 4 times 1 times a half, all divided by 2 times 1, which would be 2. So this gives me 5 over 2 plus or minus the square root of 23 over 2. That doesn't look like that'll come out very nice. So, although it's not complex, the next ones will be complex. So I guess we count our blessings here. Let's see, I lost a negative sign. That should be negative, yeah. So I've got minus 2.5 plus or minus 2.3979. I've got a decimal. So the roots are then minus 4.8979, and then when you use the addition here, you get minus 0.102. Okay. So I could say then that I could represent this, if I wanted to, as minus 3s minus 6 divided by s plus 4.8979. Yeah, because I've got that root. And then this as s plus 0.102, because I've got that one. Okay, so I've got that. So I'm now going to set this equal to, I can say this is equal to a, using a partial fractions technique, over s plus 4.8979 plus b divided by s plus 0.102. So now I have to find a and b, right? So if I multiply both sides by this, I'll come up with a. I can say in finding a and b, we've got that a is equal to minus 3s minus 6 divided by, if I multiply both sides by that, I end up with s plus 0.102, is that right? Yeah. Okay. And where am I going to evaluate this? If I multiplied both sides by that, I want to evaluate this at s equals minus 4.8979. Is that right? Is that what they're talking about in math?
You really not include b in solving for it?
Well, I guess maybe I need to take a little more time here and go through this. What I did is I took this equation here, and multiplied both sides by this term right here. Okay? So that's why I'm saying that A is equal to this. And when I multiply both sides by that, I've got, certainly I do have plus this B over here. But the B has this quantity in the numerator. That's why I'm going to set that equal to that. Do you follow that? So I mean, I'm really saying 0 times B if I want it to be. Okay. Everyone's good? Okay. So when you run through this, you let S be minus 4.8979. You come up with A being equal to minus 1.813. And we're going to do exactly the same thing here. Likewise, we could say that 0 times A plus B is going to be equal to minus 3S minus 6, this time divided by S plus 4.8979. And I'm going to be evaluating this at S equals what? Minus 0.102, is that right? So when I do that, I come up with the B, which is minus 1.187. Okay. So I'm going to take these and put those back into that form there, and let's see what that looks like. Questions of that? Am I multiplying A by 0? Oh, here? Well, when I go up and look at this expression here, I'm going to be multiplying everything by S plus 0.102, right? So B is all alone. And then A is being multiplied by this, which when I evaluate it, I'm going to get it to be equal to 0. That's just I probably skipped some steps there. That was just kind of a short way of doing that. Other questions? So if you're a little more rigorous and write this out, and when you evaluate A, multiply everything by this term, you'll get exactly the same thing here. So let's look at this guy. So we still have things in the S domain. So we've got that I in the S domain is now, instead of this awkward polynomial expression, I've got something that I can easily do the inverse Laplace transform of. So I've got A that's minus 1.813 divided by S plus 4.8979. And then I've got B that is minus 1.187 divided by S plus 0.102. And those should look vaguely familiar. We should be able to say that now, we've been trying to take the inverse Laplace transform all the way, but now we haven't something. We've got no excuse for not being able to take the inverse Laplace transform. So I take the inverse Laplace transform. I've got I then in the T domain is going to be equal to what? Minus 1.813 e to the minus 4.8979. I have too many significant figures here. And then minus 1.187 e to the minus 0.102 t. And this is all going to be u of t. So that would be our answer.
So this is essentially bringing back to the time domain from the S.
Yep. We didn't want the answer necessarily in the S domain, so I do the inverse Laplace transform. I get it back into the time domain.
What was that original equation that we used with what I have S back?
The original equation.
We just solved for the partial fraction.
we did the partial fraction expansion of this one.
Oh, okay.
Yeah. Because you'd have to be a lot better at math than me to get from this one to here. Okay. So, and this is pretty common. Sometimes our partial fraction expansion will have more terms than A and B. Sometimes we'll have complex roots. That's the next one we're going to go on to. Questions with that? So hopefully a good example. I think that was one of the homework problems. I think, in fact, that was the last homework problem. So it said to see the solutions from class lecture. So I guess we've delivered on that. So theoretically, you can finish your homework. Let's then, if there's no question, move on to another problem. Maybe we should say another challenge. This one looked a little ugly. We didn't have nice clean numbers. We had decimals. The nice thing about this is it's real. There were real roots here. Okay, things can get a bit ugly, or we can end up with complex roots, and that's where we're going next. So let's look at those complex roots. When I was talking about the inverse Laplace transform, I think I put something up like this. If we had complex roots, and there were a couple of them, but a common one that comes up is if I'm taking the inverse Laplace transform of k over s plus alpha minus j beta. And then I also have k, and this is the conjugate. That means exactly what we've used it as in the past, the conjugate, over s plus alpha now plus j beta. We could say that this is equal to 2 times the absolute value of k, which is really the magnitude of k, because k is a complex number, e to the minus alpha t times the cosine of beta times t plus theta. Okay, so we saw that in the past. That's probably one of those things just write down in your notes and continue on. But let's do better than that now. Let's use the thing. So let's try this on the following example. Let's say that we've got 100 s plus 3 divided by, and I think this is an example out of your textbook in the reading of your textbook, s plus 6. I have 6s, yeah, 6s plus 25. So that should keep us busy for a while. So let's see if we can do that. This is the one that I'm probably going to have to do some work on, right? So I use my quadratic equation. I'll have minus 6 plus or minus the square root of 36, 6 squared, minus 4 times 1 times 25. So I know right off something's got to give, right? 36 minus 100, I'm going to have a complex term. I have to divide this by 2. So we come up with minus 3 plus or minus j over 2 times the square root of 64.
Would you divide that solution?
A is 1.
C is 25.
It's just 2a.
Oh.
It was AC up here. Okay. Okay, so we tidy that up, and we recognize we have the square root of minus 64, so I take that minus out with the j. I still have the 2 in the denominator. Of course, 6 divides easily by 2. This not quite as cleanly. Let's see, square root of 64, that's what? Gives me, yeah, divided by 2 is 4. So this is not too bad. So I've got minus 3 plus or minus J4. That's good. It's complex. We're studying about complex roots, so I guess we'd expect it to be complex. Nice clean numbers. So I can say then I have roots at what? At S plus 3 plus or minus J4. Is that what my roots are going to be at? Yeah, that's what my roots should be at. So if I rewrite this, I could say then that this thing looks like this. 100 S plus 3 divided by S plus 6, no problem there. And then I factored this thing. I have S plus 3 minus J4. What's the other one going to be? S plus 3 plus J4. You all good with that?
Why does the S turn into a plus the root? Is that just because you found what S is equal to?
Right.
Okay.
Yeah. Because for this to be equal to 0, then it's the opposite side. Okay, so we're ready for partial fractions, right? So we can say that this thing is then equal to what? Maybe I'll use K. We could use A, B, and C. I don't know what they're using in math. Have they got that far yet? A, B, C? Okay. Oh, we'll mix it. I'll use K. K1, K2, K3. So I'm going to say that this is S plus 6. And then I have plus K2 over S plus 3 minus J4. Is that right? Yep. And then I have plus K3 divided by S plus 3 plus J4. And K2 and K3 are conjugates of each other. We'll see that as we go on. Okay? And we know that this is equal to this. These are equal to each other. Okay? So with that, we will solve for K1, K2, K3. Okay? So I could pull the lecture trick and say, well, solving for K1, K2, K3 and give you answers for K1, K2, K3. I'm not sure that would be appropriate, so let's spend a little more time working at that. So like I did the last problem, if I'm looking for K1, what am I going to do? Multiply everything by S plus 6. Okay, so when I multiply this side by S plus 6, that cancels out, and I am left with what? I mean, I just as well use this one here, right? So when I multiply that by S plus 6, I've got 100 times S plus 3 divided by, I'll just use that, S squared plus 6S plus 25. And that's equal to K1, isn't it? Well, I should evaluate, as long as I evaluated it at what? S is equal to minus 6. That's K1. You might say, well, what in the world happened to K2? Well, when I multiply everything by S plus 6, you multiply this and you have that S plus 6 up here. You have that S plus 6. When you evaluate it at S equals minus 6, those terms go to 0, don't they? Okay, everyone's good with that? Okay, so when we get to that, you can say that you have then, 100 times minus 3 divided by 36 minus 36 plus 25, which gives me minus 12, yeah, is equal to K1. K1's a real number, not a problem. No surprises there. So then the next go around, what are we going to do? We're going to multiply in finding K2, we're going to multiply everything by S plus 3 minus J4. So maybe I should use this expression here when I multiply that. You take that expression and you multiply by this, you end up with what? We're going to have 100 S plus 3. And then I don't want to use this one, I want to use this one because I'm multiplying by this multiplying by S plus 3 minus J4. So when I do that, that one cancels out, and I'm left then with S plus 6 and S plus 3 minus plus J4. I'm left with that one. Okay, and that is equal to K2 as long as we evaluated at what? S equals minus 3 plus J4. Isn't that right? That's the only way that I can get the no, I think it's plus J4. Yeah, I think I'm okay. So I got to go back to working with complex numbers, right? So this turns out to be equal to 100 times J4 divided by, what's this one going to be? S. Put S in for this, you'll come up with 3 plus J4, and then you're going to have a J8, which gives me, what, 50 over 3 plus J4. So I put this in a magnitude angle. This is 10 at an angle of minus 53.13 degrees. You okay with that? Well, let's see. I can cancel the J's, and I have 4 over 8, so I have 2 in the denominator. So 100 divided by 2. Okay. Now we could go through a similar process for K3, but we know K3 is equal to the complex conjugate of K2. So that means that K3 is going to be what? Same magnitude at opposite angle. Okay. Now as we get ready to move on and do use this expression here, so we're going to come back and use this expression here. I guess I need to inventory what my alpha and beta are. Let's see. This this by definition is alpha, isn't it? And this 4 is the beta. So let's make a little cheat sheet here. Alpha is equal to 3, beta is equal to 4. And then what else do we need? The magnitude of K. The magnitude of K is 10. And it looks like we need theta. What's theta equal? This was theta, wasn't it? Minus 53.13. So I think we're okay with that. So we should be able to then do this thing. So we need 2 times K, right? So when I do the inverse Laplace transform, I've got 2 times the magnitude of K e to the minus alpha t cosine beta t plus theta. So which in our case is going to be 2 times 10 . Well, I guess I better be careful with this. I've been concentrating on the complex, but we've got this one hanging around, don't we? So that's okay. Maybe I'll write one more step. So I had K1 over S plus 6. Did we come up with K1? It's minus 12. So I know that this thing in the S domain was minus 12 over S plus 6. That's this term right there. And then I had the two complex terms. So I had plus 10 at an angle of minus 53.13, and that was over, which one was that over? S plus 3 minus J4. And then I had the last one, which is the complex conjugate of that, 10 plus 53.13, and I'm dividing that by what? S plus 3 plus J4. Okay. So that's what I have. And now I should be ready to take the inverse Laplace transform. So this one's pretty easy. We've done that one before. Minus 12 e to the minus 6t u of t. And then these two, I get to use what I've learned here. I'm going to have 2 times 10, that's the magnitude of the complex terms. And then I have e to the minus, what was alpha? Alpha is 3, so e to the minus 3t cosine of beta, which is 4, so 4t. And then theta was minus 53.13, and that negative came with the theta. And that would be what, u of t. So I should be able to tidy this up a little bit and say what? I've got minus 12e to the minus 6t plus 20e to the minus 3t cosine 4t minus 53.13 u of t. So that would be our answer. So that's our partial fractions technique with complex roots. Because I took it off of the, where did we start with this? I took it off the term with the minus beta. So, which term was that? K2 had the minus beta is K2. So it'd be the angle attached to K2.
If you change your beta, then it would be, or your beta, then it would be the positive one. So if you change your beta to the minus 4, then it would be the positive angle.
If I changed my beta, Well, I mean, you could write these in a different order, but it's still then the root would be different and the answer would come out the same. I mean, it's pretty well prescribed what we have to do on this right here. So this is what the form is. The first one with the k is the minus beta, and the conjugate is the plus. So I don't have a lot of latitude in that. So I want to follow that form pretty carefully.
So we're always going to take that angle from the negative j beta side.
Mm-hmm. So again, that was a math problem. Let's see if we can do a circuit with this. Probably won't have quite as difficult of a inverse Laplace transform, but we'll have other pieces in front of it. So let's try something that looks like this. $160 volts. Quarter of a farad. That seems weird, but not as weird as a 4 Henry inductor. 4.8 ohms. We're going to close this switch at t equals 0. And we're told we have quite a bit of work to do in this problem. A couple of things that we would like to find. We'd like to find the voltage across this inductor. So I'll say that this is plus and minus V of t. We'd like to find that. And then we'd also like to find the current in this loop. Maybe I'll call this I of t. I'd like to find that also. Okay. And we're told that there's no energy stored. No. So no initial energy stored, which keeps this problem pretty easy. I don't have to go back and analyze it for time before 0. So I should be able to, if I wanted to, go right to the S domain. So we could, I mean, with this we're going to be able to say that the voltage in the capacitor at 0 is equal to 0. The current through the inductor at 0 is equal to 0. So that's done. Not have to do much work there. So I can go right to the S domain. Write this thing in the S domain. So this voltage source is going to look like this, 160 over S. And I've got this switch. Resistor will be the same, 4.8 ohms. Then the inductor. What's the inductor? That's S times L. And the inductor has a voltage source. The polarity is important on that. If you look at that sheet we developed at the beginning of last time's lecture, that is the correct polarity for the current going this way. Remember, this is going to be I of S. So that would be L times I at 0. So it's a bit of a mute issue because that's going to go to 0. Then we've got the capacitor, which is 1 over SC. And its voltage source, which again, looking at the polarity on that table that I gave you last time, would be like that. V naught over S. This is 0. That's 0. So if we had messed up the polarity, we would have got away with it, but we probably want to practice doing it right. Okay, so that's what we have. So if I look at Kirchhoff's law, I have a gain there, right? So I could say that I have a Kirchhoff's voltage law. I have 160 over S, that's a gain, is equal to, and then I probably have a bunch of drops. I have 4.8 times I in the S domain, plus I have a drop across that inductor. That's going to be S times L times I of S. And then I have this term 0. Then I have a drop across that capacitor, which is going to be what? Plus IS over SC. So let me use a little space here and continue working on this. That'll give me, when I make the substitution, 160 over S is equal to 4.8 I in the S plus S times, let's see, what's the value of the inductor? 4. And the value of the capacitor is 1/4. So I've got then 4S I of S plus 4I of S over S, right? Because the 4 in the denominator, yeah, 4I of S over S. So if I tidy that up, what do we have for I of S? We could say that we have, what, 4.8 plus 4S plus 4 over S is equal to, what, 160 over S. So I've got then I of S is equal to 160 over S divided by 48 plus 4S plus 4 over S. And that probably needs some tidying up, but I think I will leave that at that point and go on and do it in the time domain and hopefully come up with the same expression. We're certainly a long ways from done here, but I want to see what this looks like in the time domain. One thing, if I'm looking for the voltage across the inductor, that's this thing, isn't it? So this expression should allow me to solve for this current, so I should be able to get that current pretty easily, and then I'm going to have to come back and try and figure out what the voltage across the inductor is. Well, that's this thing. That's the voltage across the inductor. So we'll keep track of that term. We're probably going to come back and need to use that. Well, let's see if I can get this a different way just for good practice. So I'm going to look at this in the time domain. So in the time domain, I've got something that looks like this. 160 volts. I've got that switch that has closed at t equals 0. I've got 4.8 ohms. Got my 4 henries. And 1/4 of a farad. And I'm going to say the current around here, I'm going to say that this is I of t. This is in the time domain. So if I do Kirchhoff's law on this thing, I start at this corner, I have a gain, so there's 160, and we'll just put the u of t in there for the switch, is equal to 4.8 times I of t. And then what do we have? What's an inductor? That is L times di of t dt. Incidentally, that's an interesting term again, because that's the voltage across the inductor. If I'm interested in this voltage here, so there it is. And then I need to deal with the drop across the capacitor. I've got 1 over c times the integral of I of t dt. And then I have to add to that voltage across the cap at t equals 0. Okay. We know this is equal to 0 because we had 0 storage. This one is, what, 1/4? And this L here, that is 4. So tidy this up. 60 u of t is equal to 4.8 I of t plus 4 the I of t dt plus 4 times the integral of I of t dt. So we're ready to do the take the Laplace transform, right? So I have 160 over s is equal to 4.8 I of s plus 4s times I of s. And maybe I should be a little more careful with this one. I'd have 4s I of s minus I at t equals 0, right? And that, there's no initial energy, so that was 0. Plus then 4 I of s divided by s. Integration, that was the great bargain, right? So I've seen something like this before. 160 over s is equal to 4.8 is plus 4s is plus 4I of s over s. That's pretty close to this one, isn't it? 160 over s, 4.8 I of s, 4s I of s, 4I of s over s. So we got that. Now, I think probably this is a lot faster, but sometimes I'm a little more comfortable with the time. You can get there. It's probably important to be able to do it both ways because people will talk and present things both ways. We know that this then leads to, and I'm not going to go through this, but this would lead to what? This one over here, 160 over s. over s divided by 4.8 plus 4s plus 4 over s, right? So however you get that, whether you do it this way or whether you do it the faster way here, we got that expression, right? So let's see if we can do the inverse Laplace transform. So let me take that thing. And we've got the same expression whether we use it from here or this is written a little neater. We'll use it from there. So how can I get that looking like something that I've seen before? Maybe I'll multiply both by top and bottom by s. So what's that give me? 160 divided by 4 s squared plus what, 4 point. This was, I think 4.8, this should be 4.8, shouldn't it? Did I do the other one right? Yes, 4.8. So make sure you put that decimal there on page 8. So I had 4.8. So I got s squared 4.8s plus 4, right? And then I think I'll divide the whole thing by 4. So multiply this by a fourth and this by a fourth. So what do we come up with? 40 divided by s squared plus 1.2s plus 1. That's looking better. So now if I look at this piece here, if I factor that, I'm going to have minus 1.2 plus or minus the square root of 1.2 squared minus 4 times 1 times 1, all divided by 2 times 1. So I come up with minus 1.2 over 2 plus or minus j over 2 times 1.6. So we have minus 0.6 plus or minus j 0.8. Okay with that? So we could rewrite this thing then as 40 divided by, my terms are S plus 0.6 minus J 0.8, and the other one is S plus 0.6 plus J 0.8. Not if these are the roots, right? Because I have to put this in S to get that to go to 0, right? Yeah. Okay. So a little bit of accounting here. That's our alpha. There's our beta. Okay. So let's see. If I use partial fractions on this, I'm going to say that I have, this would be equal to K1 divided by S plus 0.6 plus J 0.8. Sure I got that right here. Yeah. And K2 divided by S plus 0.6 plus 0.6 minus J 0.8. Yeah, I think I should be okay with that. Do I want to do those the other way? No, I think I should do those the other way, shouldn't I? So I think I'll make this positive and that negative. There. So anyway, when I go through and I find K, for instance, K1 is going to be what? If I multiply both sides by this, so I'm going to have 40 divided by I'm going to have the other one, so I'll have the positive one. Yep, that's what I want. Plus 0.6 plus J 0.8. Yeah. And I'm evaluating this then at S is equal to minus 0.6 plus J 0.8, which gives me then 40 divided by J 1.6, I think. Yeah, J 1.6, which is equal to, throw that in your calculator, you come up with 25 at minus 90. Okay, so that's K1. So K2 would have to be what? 25 at plus 90. Okay. So the only root we have is the complex root, so we can really just go right to the solution. And I go back to page number 5. And we'll look at our solution right here that we used before. Let's see how that works out. So we said that this would end up being 2 times k, the magnitude of that, e to the minus alpha t times the cosine of beta t plus theta. So what do we have for our alpha? We said that alpha was 0.6. We said that beta was 0.8. What do we say k was? 25. Okay, so let's see how that works. We've got then 2 times 25 e to the minus 0.6t times the cosine of 0.8 t minus, oh, we didn't do theta, did we? This is going to be our theta. So our theta is minus 90. So there's our minus 90. So we've got then 50 e to the minus 0.6 t. And we could write out the cosine, or this cosine at minus 90 is really what? Sine 0.8 t. I should add a u of t there. We'll have a u of t there. So that would actually be our answer. So let's make sure we didn't make this more complicated than it need to be. The cosine of 0.8 t minus 90 is just equal to the sine of 0.8 t. So just simplified that a little bit. So that's I of t, isn't it? So that got that part done. We were looking for I of t. We were looking for this current here, right? Well, that's only half the problem. We're still looking for what? V of t, aren't we? So we're still looking for V of t. And there's a couple different ways to do it. We have I of s, so we could pursue this way, because we know that V in the S domain is going to be equal to S times L times I of S. We have I of S. That was just before we did the inverse Laplace transform. Or, let's see, is there another way that we could do it? Yeah, back here. Well, I think I got my page numbering mixed up. This should be 10. L di dt, and that's v in the time domain is equal to L times di dt. Okay. So we'll tackle both those ways in the future and see if we come up with the answer. Let's see, what is I of s? Do we have an expression for that? That was equal to, back here we could say that that was 40 divided by s squared plus 1.2 s plus 1, right? And what was I of t? Yeah, there's I of t right there. So I have to do a little calculus with that. So that should be a good place to start next time. I'll record that lecture tomorrow, and that'll be available for you to look over as we start to get this subject finished up.